So yesterday I ended my challenge in Advent of Code. I decided to end it in day 17 because initially I said to myself that I will go and do Advent of Code up until like February or the beginnings of February because I was convinced that I could in time make it. However, day 16 proved to be very hard and I didn't want to use so much of my time to do something that was supposed to be fun and it started to get tedious and I didn't want to keep going. Therefore, I end my challenge prematurely on day 17. I got a little bit of DSA review. I haven't touched DSA since college, so it was nice. Wasn't the greatest thing ever, but hey, some BFS, some DFS. If I remember how you would lay this down, could be fine. It's not like I'm gonna use it on the job, but you may never know. Life always holds nice stuff out. What I would want to discuss today, I did it in Rust, but I'm gonna keep Rust out because I'm still using it till all the February. Get under my belt a couple 3-4 months. So I would like to share those opinions in February or at the end of the February. In the meanwhile, I'd like to discuss what was like this Advent. Was more specifically the days I remember the most and the one that hurt me the most. Starting with day 4, which wasn't really that bad as an idea, but it was funny because I had to get into some algebra. Basically, the task of this day was to count how many Xmas words were there and some X. Basically, Xmas and Xmas on the on backwards. The input was a matrix of words. And the problem I had encountered was I use a regex, so anytime you would want to have something like intersecting, this should be counting like 2 words. However, using regex means that I couldn't, or at the very least that my knowledge of regex wasn't that easy to conjure this. And the solution for that was to just put everything in an array, and let's say it's O to N, and then reverse it. This basically guaranteed me that I could find every instance of Xmas and some X. And that worked nicely for the rows. For the columns, I just transposed the matrix. So that works the same way. And the last issue was the diagonal. So in the case of a diagonal, I had a little problem because if I were to start doing now a parser, it will invalidate all of my work. So I wanted to reuse the functions from this. Thanks to a friend of mine, I got a nice suggestion, which was you just lay down as rows the matrices, which works nice with everything done beforehand. Therefore, I don't quite can explain the code used because it's non-trivial. So essentially what I did was iterate over every row and column, and each outer loop you would move one ahead, dropping anything that's below 4 letters because Xmas is 4. So any element below 4 gets auto dropped, everything else is in, and we use the same code. So this was day 4. Not that difficult, but I found it nice and it gave me a little bit of a problem. Okay, day 6. Again, not particularly tough, but I remember having a slight difficulty. Also performance issue. Basically, this time we had, again, a grid. You can imagine it like a labyrinth, where there were obstacles and a guard. Every time that the guard hits an obstacle, the guard had to always rotate to the right. the first part asks you to find the exit. This will count as an exit. So when the guard hits a border, he exits. And this was okay, part 1. Part 2 asks you to place a wall so that the guard will be stuck in a loop. Now, this one wasn't that hard, except that my program took for a long time, which I was surprised because Rust is very fast. My supposition is that I was creating a bunch of memory and that slowed me down because I'm running it in Linux native, so that should be the fastest experience ever. I'm not on VSL or anything like that. But I was still fresh on Rust, so my guess is I did some oopsie daisy somewhere. In order to optimize this solution, thanks to that, I first decided that since you can't really place more than one block at a time, I would just take what was, let's say that this one is the path that the guard will lead. Then I decided to add a block inside this path, because there's no reason to run it for every single point, because this would be a matrix. Every point that's walkable on the matrix doesn't necessarily mean that it will be worked by the guard. And you can add only one piece at a time, which means there's no need to check what happens if I put a point over here, because nothing will happen. Another optimization I thought to think was, hey, there's no need for me to walk everything because the loop detection works in a simple manner. Given a position and given a direction, let's say up, if I hit the same position with the same direction, that means I hit a loop. My supposition was, once you hit a loop, it does not matter where I start. I should always hit a loop. So if I'm over here and I get a loop looking like that, sooner or later I will understand that it's a loop. Which meant that I don't need to always run from the starting point, but I could always run from the point before the wall. This supposition, I didn't check how, but it was wrong. It gave me a result which was -1. So that was fun to debug. And generally it was a problem of, it was slow. So asked a little bit of optimization. Nice day, wasn't particularly hard, but it was memorable to me. So day 12 would be a bunch of letters, let's say like A, B, C. These letters would form plots of lands because every letter is a plant and every contingent letter is a plot. Case in point, if we add A over here, this is a different plot from the 3 A's on the top. And you would end up with something like that, let's say. Each quadrant would be his own land. The first part of the problem asks you to multiply area times perimeter, and this will be equal to the cost of the fence of every plot. So you want to find the total cost. The second part, however, asks you to find how many sides are there to each plot. And this problem was more difficult. I had 3 approaches before I got it right. My first approach was to check the changing of a direction. Basically, any change in direction would count as a plot, would count as a side. However, that's not necessarily true because not every change of direction is made the same. Case in point. In such situation, this would work nicely, but that's only when the fence don't overlap. Let's suppose that your fence works like this, and this is a double overlapping fence. In this case, this will count as 1, the fence on the left, the plot on the left, 2, this little point here, and 3, the plot on the bottom. So in this case, this algorithm will fail. Another algorithm that I thought would be simpler to improve would be corner style counting. So for non-complex geometrical figures, there would be as many corners as sides, which again would work essentially most of the times, but sometimes you could have some things like this. And in this case, we'll have one side over here. In this case, the sides are way more because you have one over here, 2, 3, 4, 5, 6, 7, 8. So this plot will count 8 sides. But if you were to count the corners, you will count 1, 2, 3, 4, and 5. So this caused me a lot of trouble. Both of them I tried to add extra conditions. In that case, I would assume adding some extra conditions will always get you farther, which did for a while here, but stopped quite quickly. And did for very long with these methods. I just add some stuff like, hey, if you have some conditions like more than one, like in this case, I set him to count +2. Or when you had 3 adjacent, I had to ask +1. However, there was a bit of a problem. Let's say you have a plot like this. And that would mean that these are 2 separate lines. So this should be counting like 8. However, my method always worked on the fence, so I couldn't understand the difference between 2 different fences standing in a vertical. My problem counted 7. And that was disheartening because I believe I stayed on this problem for like 3-4 days. But thankfully, my man Sol, this guy over here, did give me a hint, which would basically be, if you take a look at this animation, it first counts the rows, the sides on the rows, and then the sides on the vertical. And thanks to this gift of animation, I stand for the third method, which would basically be, instead of counting the fence, I would count every adjacent and I would count rows and columns. So my algorithm basically started to, let's give a simple example, and would basically check every vertical and horizontal. And this worked like a charm, was very easy to implement and very easy to do. And that ends up the day 12. Day 14 would be one of my favorite ones. I'm not gonna lie, this was absolutely hilarious because day 14 would have again a grid with some robots. So every robot can move everywhere at any time. Each quadrant can also hold more than one robot. So we would say 1 would be 1 and 3 would be 3 robots on the same plot. And the first part basically was an animation. You would go frame by frame, move the robots in a series of directions, which were written like that. So you parse this out, move the robots, and everyone is happy. So part 2 asked to find a Christmas tree, or rather a frame in which a Christmas tree would happen. I believe the frame were about 10K, so watching them one by one wasn't necessarily possible, because if they're going very slow, you would end up watching the whole day, hours. If it was too fast, you will miss it. Therefore, the possible ways in which could be done, I heard people do a lot of creative stuff. That's why I like this job. This was the day that I believe added more creativity than every other day. My solution was very simple. Basically, I would BFS on every frame, on every robot, and if I found some significant agglomerate of robots, which since the wording was most, I believe it would have to be 51%, or would say more than 50%. That's what I would understand as most. My supposition was correct about them being 51% robots to make the picture. It wasn't correct that all 51% of robots are contingent. That was because the tree had a frame. So that's the big deal that made me miss. Therefore, I just BFS and printed out the max numbers of contingent trees, which will end up be like 49% of the total, and print that out. By the way, hilariously enough, I used emojis to keep track. So everything that was found, since I'm from Italy, had the what do you want sign. So this was the picture of the tree with the emojis. This was a fun day. Honestly, I don't see it being that difficult. It sparked creativity and it wasn't really that hard. And now time for the day that managed to burn me out. So day 16, this was the biggest of the problems because day 16 was a maid's escape kind of algorithm. So again, our to the grid, we have an exit, we have a starting point, there would be no obstacles on the way, and you will have to find the exit. You have also to find the most or the least expensive exit, because every time that you change direction, you would pay 1,000, and every time you move, you pay 1. If you move and change direction, that's 1,001 basically. And the problem with this was, I knew that BFS could work. You could basically BFS everything into an array and then compute how much it costs and keep the lowest, so keep the mean. This would have been perfectly fine, but my viewers on the stream suggested me to check out A star because I nominated Dijkstra, and I thought to myself, well, Dijkstra could work fine. And my viewers explained to me that A star is meant for this kind of stuff. And A star, in my understanding, is basically Dijkstra plus a heuristic function. The simplest way to say a heuristic function is that this adds bias to our search, which would mean that if I move out, so say AS, if I'm moving over here, that means I'm getting farther away. But if I move over here, my heuristic will guarantee that I'm moving better. And this will allow to find faster the exit. Now, this was for part 1. For part 2, it was asked to find every possible best path. And this could happen in a couple of manners, but my supposition was that if I move, let's say this is the best path, then maybe there would be some alternative paths that cost the same, have the same amount of turns. So if I check every neighbor and add up the cost that you have over here plus the Dijkstra or A star algorithm starting from here, then I will be able to understand if it's the same as my most optimized solution, then we're fine. Otherwise, that's going to be dropped. And this approach ended up working, but I had a couple of problems to fix. Problem number 1, I was finding 6786 or half of my solution, which was weird because that invalidates my supposition. That meant that there were some, let's say this is the best path, there had to be some other best path that wasn't on the same track as this, because my solution was 124. I downloaded someone else's code and checked it out just to be sure, because I was kind of lost. And in doing so, I seen that, let's say that this is my best solution, their best solution had maybe something like this going, meaning that their best solution was not following my best path. In fact, their best solution was correct and mine had something a little bit longer, and this path was dropped, which was weird. And I started to look in my implementation for Dijkstra, And the problem for my implementation for Dijkstra was very simple. I had never accounted for the direction. And there was this one kind of makes me salty problem. Basically, suppose I work in this manner to get here. And suppose I work in this other manner to get here. Now, these two roads cross. My horizontal road would cost 4k at this point. And my vertical direction would cost 3k at this point. Now, the funny thing is that my 3k, when we get in the end, would end up costing 4109 in our example. But the other one will be 4103. So, this way is shorter. Why was that? Well, simply because this point will be overwritten by 3k, and you will never look back if it was better, because it wasn't and the node was already seen. So the way to fix this is, instead of saving from my visited node only the ones that already had happened, I would have to save not only the coordinates, but I would have to save the coordinates and the direction. This way it will be run through everyone. It asks more cycles because you couldn't just return when you find the E. Because my green path will walk till the E and result in this. Then we will finish this path and get the correct result, which will override everything else. And this worked fine and outputted 985 out of 124, which is still wrong. And this was wrong essentially because, actually very easily, because I had a bad supposition. So let's move it out. My supposition was that there would be only some little paths like this one that would deviate. However, there could also be a double deviation, and I was never checking for this guy. Well, not a big deal. You're just gonna add, make sure that every time you visit something like this, you put it in your queue and you keep going. And that was correct, but when I implemented this change, I had like 4,000 out of 124, and this was a simple programming goof up because instead of adding the partial cost, I only added the cost of the new run. So if this was the new run, I added the new cost, but I forgot to add the cost up until now. This was a silly goof. The combination of these bugs took me 2 weeks to realize. I was pretty burnt out and I was done. I tried to do day 17, but day 17 asked you even more of tedious debugging, and I was not gonna work on that. Not up until January. I really didn't like the idea of keep going for the advent. I was satisfied with Rust learning. I was satisfied with the review of algorithms. So I'm fine. As I said, my opinions on Rust will be held up at the moment. I will take a look later on. I'm gonna make a video about February. Thank you for listening. You can watch the code, will be in this description. It has been done in Rust and a couple of days in Ruby, just because. And I see you in the next one. Bye.